It's just being so slow. Okay, watch my phone. It's freaking out. If I suddenly stop recording, let's try and catch it. Yeah, I can't believe we just lost all that. All right, make sure it doesn't magically flip off. Shoot. Well, I have my other calculus series recorded, so you can go into lecture 2, see where I talk about the positivity axioms if you get confused. Should have covered the exact same material. So it's up there, it's just you're going to have to go to my lecture series to find whatever you missed there if you have questions about positivity. Sorry. So moving on, interval notation. Similar to what we already said. So A, B, when you see an interval like this, what does that mean? That means all the numbers between A and B, not including A, but including B. All the x greater than A and all the x less than or equal to B. Another way of saying it. When you see it like this, what's that? That's all the numbers between A and B, including A. When you see a notation like this, this is all the numbers greater than or equal to A. Now you notice we put that infinity symbol in there. It's worth noting, infinity is not a real number. So we can't include it in the interval. So when we introduce infinity, it's only to help make sense of this kind of notation. So when I say A, comma, that crazy symbol, all I'm saying is all the numbers greater than or equal to A. Make sense? Similarly, when I say negative infinity, what do I mean by that? I mean, we're going to the left without end. So this is a way of saying all the numbers less than or equal to B. This is all the numbers greater than A, not including A. This is all the numbers less than B, not including B. This is how we specify all the real numbers. Good? Is that throwing you off? Are you good with up here? Okay.
Why are the infinity signs in different spots?
So when I'm saying, so let's go back to the first one. So I'm saying all the numbers from A to infinity.
Okay, so because it's negative?
Here I'm saying all the numbers from negative infinity to B. So if we draw a quick number line, get a marker. Here's our number line, here's 0. And we can go off. Positive infinity is clear out there, negative infinity is clear out here. So when I say all the numbers from A to infinity, A is some number, we don't know where it is, it's somewhere on there. We're saying all the numbers starting here going on forever that way. When I say all the numbers from negative infinity to B, B is some number, we don't know where it is, doesn't matter where you pick, B right here. We're saying all the numbers starting here going that way.
That's not what it's saying, though.
This?
Yeah.
This is saying all the x where x is less than or equal to B. So let's say B is 5.
Starting at B.
Oh,
Or
sorry.
does it matter?
I probably shouldn't have said starting at, because you want to start at the left and go to the right. Okay, so forget starting at. What does this mean? It means this exactly right here. All the numbers less than or equal to B.
Right.
This means all the numbers greater than or equal to A. This means all the numbers greater than A. This means all the numbers less than B. This means every number. And then when we have square bracket the same number twice, that means the set of just that number. Any question on any of those intervals? Is my camera still going? Nothing weird? Okay. So that covers preliminary stuff. And now we're ready to start section 1.1. Now, section 1.1, we're going to work our way up to the completeness axiom, but the first thing we're going to introduce is a set, or the notion of a set being inductive. So we're going to be looking at subsets of real numbers and determining whether or not that subset of real numbers is inductive. Now, from discrete math, you might be thinking inductive sets are natural numbers. That's not necessarily the case, and we'll get to the definition of natural numbers. Let's see right here.
But an inductive set that includes one is.
So let's go over what exactly the inductive set is and give you a high-level intuition for it. So let's say I've got some set of numbers A here, and I don't tell you what's in A. You're trying to figure out as much things in A as you possibly can. But I tell you two things about A. One, I tell you that the number 1 is in A. So now, you know at the very least, hey, 1's in A. But say I tell you that if K is in A, where K is some number, that implies K plus 1 is also in A. So now what do you know is in A?
All the natural numbers.
You know that A at least has 1 in it, right?
Right.
That's from this.
It has
But
one.
you know that anytime K is in A, K plus 1 is also in A.
Right.
So, you know that 2 is in A.
But we haven't defined 2.
Right. You know that 1's in A, and you know that that means 1 plus 1 is in A. And we'll write that symbol as 2. And you know that 1 plus 1 plus 1 is in A. Since 1 plus 1 is in A, 1 plus 1 plus 1 is in A, or 3 is in A. And so you know that 4 is in A, and 5, and 6. Suppose I gave you some other information. Pretend we know all about numbers. What if I told you, okay, 1/2 is in A? Okay, now you also know that 1/2 is in here. What else do you know is in there now?
3/2.
Since 1/2 is in there, then you know 1/2 plus 1 is in there, and so 3/2 is in there, and 5/2 is in there, etc. And what if I told you, okay, 0.1 is also in A? Now what else do you know?
1.1 is.
1.1 is in A, 2.1 is in A, etc.
Okay.
Okay? So now you got that, let's go over exactly what an inductive set is. A set S is inductive, provided that two things are satisfied. First condition, 1 is in the set. And second condition, if X is in the set, X plus 1 is in the set. Okay? So first off, I told you A was inductive, and you were telling me information about it. And then as I gave you more information about A, since you knew it was inductive, then you were able to tell me even more things in the set. Right? So let's look at some examples of inductive sets. Here's an inductive set. -3/2, -1, -1/2, 0, 1/2, 1, 3/2, etc. Follow the pattern counting by halves. Is this an inductive set?
No.
Yes, it is. It satisfies both the conditions. First condition, is 1 in the set?
Yes.
Yes, it's right there. Second condition, is it true that every time X is in the set, X plus 1 is also in the set?
Yep.
Yeah. If -3/2 is in the set, so is -3/2 plus 1. For any number you pick in the set, that number plus 1 is also in the set.
What?
But you don't.
Exactly what we did over here. Once I told you 1/2 was in the set, you instantly knew all of that information. Pick any number you want in the set. Pick any number X. Is X plus 1 also in the set?
But how do you have an idea of the? So, what, like with the natural numbers, you know that it starts at 1 and then it continues going backward. With negative numbers, how do you know where to start? Because you can't.
Okay,
go backwards.
maybe you're not used to this notation, sorry. So when you do the 3 dots,
Right.
that means continue going in the negative direction following the pattern that appears obvious.
Obviously.
And when I have the 3 dots going that way, it means continue in the positive direction forever.
I understand that. I'm wondering how do we represent that with what we know about an inductive set?
Well, my examples aren't going to be only using the information that we already know, because the point is, with examples is, go to information you're comfortable from other classes to help you get intuition for the idea.
Okay.
So for example, I'm telling you that the integers are inductive set, or I might say the natural numbers are inductive set. We haven't defined what those sets are in this class yet. That's just to give you high level understanding.
Okay.
Same way that I'm writing all these numbers, that we haven't defined what they are. Now we're probably not going to do it with all those because, well, we could, but doesn't matter. Okay. So, does it make sense that this set is an inductive set? You need to check two conditions. One, is 1 in the set? Yes. 2, is it true that for every number in the set, that number plus 1 is also in the set?
You probably should have put 2 in there.
Should have gone to 2?
Yeah.
So 2 is the next number that comes here, negative 2 is the next number that comes here. So, yeah. Well, let's look at the integers. Are the integers inductive?
Yeah.
Yes. 1's an integer, and for any integer, if you add 1 to it, it's still an integer. So the integers are inductive. What about this set? All the numbers starting at 0 to infinity.
Yeah.
Are those an inductive set? You sure?
Yes.
Okay, let's try this one. All the numbers starting at 1 going to infinity. Is that an inductive set? Yes. Are all the real numbers an inductive set? Yes. If I take a real number and I add 1 to it, it's still a real number. That's going all the way back to basically the first thing we said. One of our assumptions about addition. A real number plus a real number is always a real number. So a real number plus 1 is still a real number. What about the rationals? Are the rationals inductive?
Well, rationals are a subset of the reals.
Well, yeah, everything's a subset of the reals here.
Yeah.
Just because a set's
Yeah.
inductive doesn't make it subset inductive.
Yeah.
Because a set just containing 1, that's a subset of the reals. That set is not inductive.
So am I right? So an inductive set must carry on forever in like the right direction, like to infinity, but it doesn't have to in a left direction.
Correct.
Okay.
It can't have the biggest element in there.
Right.
Because if k is in there, k plus 1 has to be in there.
Right.
So assume that k was the biggest element in there, well, then k plus 1 also has to be in there, showing that it can't have the biggest element. So, yes, it can't have the biggest element. Okay, so there's infinitely many inductive subsets of the real numbers. Right? Notice all of these are subsets of the real numbers. Every set of numbers we're going to talk about in this class is going to be a subset of the real numbers, since real numbers are a subset of itself. We're either going to be talking about the real numbers or some subset of the real numbers. Good? Okay. So now we can define the natural numbers. What are the natural numbers? The natural numbers are the intersection of every inductive subset of real numbers. Or in other words, since we're always talking about the real numbers, the natural numbers are an intersection of every inductive set. Take the intersection of this, with this, with this, with this, with this, with this, with every single inductive set that there is. Take the intersection of all those. And that's the natural numbers. Am I losing you in any of that? Will you remember what the intersection is? What do we mean when we take the intersection of a bunch of sets? We mean we're only taking the elements that are in every single one of those sets. The natural numbers are the numbers that are in every single inductive set.
That makes more sense why he defines it without 0 then. Because in discrete math it has 0. In this case, if that's the definition of natural numbers, you can't have 0.
Right. So if you're coming at it, defining the natural numbers in terms of the real numbers, it seems very natural to not have the 0 in there. If you're constructing the numbers and you're working your way up, it's very natural to have 0 in there.
Yeah.
So yeah, some books have 0 in the natural number, some books don't. In this book, we do not have 0 as a natural number. Because 0 is not in every inductive set. For example, this. 0 is not in there, and this is still an inductive set. So the natural numbers are a subset of every inductive set. They're the intersection of every inductive set. So what are the numbers that are guaranteed to be in every inductive set? It's the numbers that you were listing out right here before we did this. What do you know about every inductive set? You're guaranteed two things. If it's inductive, 1's in there. And if it's inductive, every time 1 is in there, 1 plus 1 is in there. And since 1 plus 1 is in there, 1 plus 1 plus 1 is in there, etc., etc. Make intuitive sense?
So the natural numbers are just like 1, 2, 3, 4.
Yeah, they're just 1, 2, 3, 4, 5, 6, 7, 8, etc. They're all the numbers that you could get following this pattern starting at 1. 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1.
How do you prove that?
Well, that's the next thing that we're going to do is we're going to prove n is inductive.
Not prove that n is inductive. I mean, prove that n doesn't include things that are outside of what we know as the natural numbers. Because it's the intersection